At the end of this video, you should be able to list the 6 basic steps used in writing Lewis structures, explain how to determine Lewis structures for molecules containing single bonds, multiple bonds, or both, and explain why scientists use resonance structures to represent some molecules. Chapter 6, Section 2, Electron dot notation. Covalent bond formation usually involves only the electrons in an atom's outermost energy levels, or the atom's valence electrons. To keep track of these electrons, it is helpful to use electron dot notation. Electron dot notation is an electron configuration notation in which only the valence electrons of an atom of a particular element are shown, indicated by dots placed around the element's symbol. The inner shell electrons are not shown. In general, the element's number of valence electrons can be determined by adding the superscripts of the element's noble gas notation. The electron dot notations for elements with 1 through 8 valence electrons are written as shown in figure 6-10 on page 170 of your text or on the screen now. Follow along with these sample problems, which are also on page 170 of your text. A. Write the electron dot notation for hydrogen. B. Write the electron dot notation for nitrogen. Solution for A. A hydrogen atom has only one occupied energy level, the n is equal to 1 level, which contains a single electron. Therefore, the electron dot notation for hydrogen is written as shown on the screen now. Solution for B. The group notation for nitrogen's family of elements is NS2, NP3, which indicates that nitrogen has 5 valence electrons. Therefore, the electron dot notation for nitrogen is written as shown on the screen now. Lewis structures. Electron dot notation can also be used to represent molecules. For example, a hydrogen molecule, H2, is represented by combining the notations of 2 individual hydrogen atoms. The pair of dots represents the shared electron pair of the hydrogen-hydrogen covalent bond. For a molecule of fluorine, F2, the electron dot notations of 2 fluorine atoms are combined. Here also, the pair of dots between the 2 symbols represents the shared pair of a covalent bond. In addition, each fluorine atom is surrounded by 3 pairs of electrons that are not shared in bonds. An unshared pair, also called a lone pair, is a pair of electrons that is not involved in bonding and that belongs exclusively to one atom. The pair of dots representing a shared pair of electrons in a covalent bond is often replaced by a long dash. These representations are all Lewis structures, formulas in which the atomic symbols represent nuclei and the inner shell electrons. Dot pairs or dashes between 2 atomic symbols represent electron pairs and covalent bonds, and dots adjacent to only one atomic symbol represent unshared electrons. It is common to write Lewis structures that show only the electrons that are shared, using dashes to represent the bonds. A structural formula indicates the kind, number, arrangement, and bonds, but not the unshared pairs of the atoms in the molecule. For example, on the screen now are the structural formulas for F2 and HCl. The Lewis structures, and therefore the structural formulas, for many molecules can be drawn if one knows the composition of the molecule and which atoms are bonded to each other. The following sample problem illustrates the basic steps for writing Lewis structures. The molecule described in this problem contains bonds with single shared electron pairs. A single covalent bond, or single bond, is a covalent bond produced by the sharing of one pair of electrons between 2 atoms. Follow along with this sample problem, which is on page 171 and 172 of your text, to learn the 6 steps to draw Lewis structures. So draw the Lewis structure for iodomethane, CH3I. Step 1. Determine the type and number of atoms in the molecule. The formula shows 1 carbon atom, 1 iodine atom, and 3 hydrogen atoms. Step 2. Write the electron dot notation for each type of atom in the molecule. Carbon is from group 14, therefore has 4 valence electrons. Iodine is from group 17 and has 7 valence electrons. Hydrogen, we know, has 1 valence electron. Step 3. Determine the total number of valence electrons in the atoms to be combined. Step 4. Arrange the atoms to form a skeleton structure for the molecule. If carbon is present, it is the central atom. Otherwise, the least electronegative atom is central, except for hydrogen, which is never central. Then connect the atoms by electron pair bonds. Step 5. Add unshared pairs of electrons so that each hydrogen atom shares a pair of electrons and each other nonmetal is surrounded by 8 electrons. Step 6. Count the electrons in the structure to be sure that the number of valence electrons used equals the number available. Be sure the central atom and other atoms besides hydrogen have an octet. There are 8 electrons in the 4 covalent bonds and 6 electrons in the 3 unshared pairs, giving the total correct of 14 valence electrons. Multiple covalent bonds. Atoms of some elements, especially carbon, nitrogen, and oxygen, can share more than 1 electron pair. A double covalent bond, or simply a double bond, is a covalent bond produced by the sharing of 2 pairs of electrons between 2 atoms. A double bond is shown either by 2 side-by-side pairs of dots or by 2 parallel dashes. All 4 electrons in a double bond belong to both atoms. In ethene, which is C2H4, for example, 2 electron pairs are simultaneously shared by 2 carbon atoms. A triple covalent bond, or simply a triple bond, is a covalent bond produced by the sharing of 3 pairs of electrons between 2 atoms. For example, elemental hydrogen, N2, like hydrogen and the halogens, normally exist as diatomic molecules. In this case, however, each nitrogen atom, which has 5 valence electrons, acquires 3 electrons to complete an octet by sharing 3 pairs of electrons with its partner. This is illustrated in the Lewis structure and the formula structure for N2, as is shown in example 1 on the screen now. Figure 6-11 on page 173 of your text, or on the screen now, represents nitrogen's triple bond through orbital notation. Like the single bonds in hydrogen and the halogen molecules, the triple bond in the nitrogen molecules is nonpolar. Carbon forms a number of compounds containing triple bonds. For example, the compound ethine, which is C2H2, contains a carbon-to-carbon triple bond. Double and triple bonds are referred to as multiple bonds or multiple covalent bonds. Double bonds generally have higher bond energies and are shorter than single bonds. Triple bonds are even stronger and shorter. In writing Lewis structures for molecules that contain carbon, nitrogen, and oxygen, one must remember that multiple bonds between pairs of these atoms are possible. A hydrogen atom, on the other hand, has only 1 electron and therefore always forms a single covalent bond. The need for a multiple bond becomes obvious if there are not enough valence electrons to complete octets by adding unshared pairs. Sample problem 6-4 on page 174 of your text illustrates how to deal with this situation. Table 6-2 compares average bond lengths and bond energies of some single, double, and triple bonds.
Single covalent bonds are formed when 1 pair of electrons is shared between 2 atoms, as shown in this molecule made up of 2 atoms of fluorine. The dots represent electrons. The shared electrons can be represented with a line. This is often simplified to a single dash, representing a single bond between the symbols for the elements involved. Double covalent bonds are formed when two pairs of electrons are shared between two atoms. Again, each set of shared electrons can be represented with a line. Double covalent bonds are usually shorter and have higher bond energies than single bonds. Triple covalent bonds are formed when three pairs of electrons are shared between two atoms. Each set of shared electrons can be represented with a line. Triple bonds are usually shorter and have higher bond energies than single or double bonds. Some molecules and ions cannot be adequately represented by a single Lewis structure. At one time, it was theorized that the bonds in molecules like ozone resonated or alternated between single and double bond states. Later investigation proved that the two bonds were actually identical. The resonating bonds never existed as pure double or single bonds, but as something in between, both with respect to bond length and strength. The electrons in these bonds were somehow shared evenly across the structure. Electrons shared in this way are said to be delocalized. Resonance is frequently represented by two Lewis structures joined by a double-headed arrow.
Covalent network bonding. All the covalent compounds that you have read about to this point are molecular. They consist of many identical molecules bound together by forces acting between the molecules. And you will learn more about intermolecular forces in section 5 of this chapter. There are many covalently bonded compounds that do not contain individual molecules, however, but instead can be pictured as continuous, three-dimensional networks of bonded atoms. You'll read more about covalently bonded networks in chapter 11. At this point, you should be able to list the 6 basic steps used in writing Lewis structures, explain how to determine Lewis structures for molecules containing single bonds, multiple bonds, or both, and explain why scientists use resonance structures to represent some molecules.